My apologies.
Okay, we're good?
Yeah, we're good.
And so on your pre-lab graphs, all of your graphs, all of your groups had that, and I signed off on it. Guess what your graph should have looked like when you got done drawing it? That. There's a whole list of things that you had to describe underneath it. I said, here are the things that you need to do. Label the sign of velocity and acceleration. Tell me when it's speeding up or slowing down. Tell me when it hits. Tell me when it compresses. Okay? So here's a general word of advice. Grant me the, whose phone is dinging? Someone's phone is dinging. If it dings again, I'm going to turn that thing into a projectile. I'm just saying.
My phone do not disturb.
I thought I turned it. Let me check. I don't know.
Okay. So here's the drill. And this, grant me the wisdom from 52 years on this earth. If you want to be successful in life, in a job, whatever, pay attention to the little things. Your boss is not going to trust you with anything big if you can't handle the little things. If you want to drive the boss nuts, screw up the little things. If the boss says, hey, I need you to do this, and gives you a list, okay, and you don't do it, what's going to happen? You're going to get fired. At best, you're going to be stuck at the lowest rung job that exists in that company. Because if you cannot be trusted with the little things, they're not going to trust you with the big things. You got to be successful in life. It boils down to showing up, working hard, paying attention to the little things. Everything else will take care of itself. Okay? Trust me. And I'm not saying this to brag, but I don't have a wall full of national teaching awards because I do things half-ass. You pay attention to the little things, everything else will take care of itself. Okay? So whether it's using a ruler, whether it's paying attention to the details, those things matter. And the sooner you develop this work ethic that says, hey, I'm going to take pride in what I'm going to do, and I'm going to make sure I do it right. That's the biggest attribute that you can have. Everything else will take care of itself. Okay? So when you get these labs back, some of you are, it's a train wreck for some of you. I'm going to be honest. It was an absolute train wreck because you didn't follow the instructions. You didn't think things through. So I spent a lot of time and a lot of ink on some of your papers correcting them. And I promise you, on the test tomorrow, there's going to be questions over this lab. I promise you. So you better figure out what went south on these labs. So anyway, so let me hand that back. So that, you know, my tirade. All right. So let's talk about the assignment from yesterday. All right. Anybody have any specific questions you want me to go over? Now, let me go over what I did. So let's talk about the one where you have C plus F. So this is on number 5, we're going to do C plus F, okay? So this is what I would do, okay? If you gave me those two vectors and said, hey, I want you to add these two things together. Okay, cool. This is what I would do. First thing I would do is I would just draw it as a free body diagram so I have some idea what's happening. So these are two acceleration vectors. So I got one is 195 degrees, which puts me somewhere down in here, right? So I got 4.76 meters per second squared, 195 degrees. Then that's C, and then I got F at 350, which puts me somewhere over here, right? And that's 2.5. Now, based solely upon this, okay? Just based solely upon this, drawn as a free body diagram, between what two values does my angle have to be for my resultant vector?
Between 195 and 350.
It's got to be somewhere between 195 and
350.
350. Okay, so this is over here at 350. So 4.76 is the bigger one, 2.5 is the smaller one. So do you think it's going to be closer to 195 or closer to 350? 195. Closer to 195. So right away here, when I give this answer, I know beyond any doubt that that angle has to be between these two values. Okay? And if it's not, I've done something wrong. So I haven't even touched the calculator. All I'm looking at is the big picture. So when you get into these problems, here's one of the things you've got to be able to do. Don't get so wrapped up in going, oh my God, I'm going to get my calculator and I'm going to follow these steps. Step back. See the forest. Okay? Worry about the trees later. Figure out the lay of the ground on the forest. Now, on the test tomorrow, I promise you, you're going to have 3 different problems involving vectors. And here's going to be the sequence. The first one, I'm going to lay it out. I'm going to say, here are these vectors, and you're going to draw it tip to tail using your protractor and ruler. That's going to be the first one. Second problem is, I'm going to give you one single vector, and I'm going to ask you to find the x and y components of it. That's going to be the second problem. Third problem is going to be one like this, where you're going to have 2 vectors, and you have to find the result. That's going to be the sequence. Okay, and it's going to go in that order. Okay, I'll tell you the sequence of that page. The first question up there on the top of that page is going to be, hey, what's the difference between a vector and a scalar quantity? And you're going to say what? A scalar quantity only has
Magnitude.
and you want to use the word while a vector quantity has
Magnitude and direction.
And if you don't remember what a vector quantity is, oh, look, it's up here on the board. Okay? And yes, I know it's up there. Oh, Mr. Burkham, did you know you left it up there? Oh, yeah, I do. Okay? So don't act like, oh, Mr. Burkham doesn't know it's there. Yes, I just don't want to cover it up. It's not worth the hassle. Okay. So, you're gonna have a problem like this. Here's my word of honor. When you go to work this problem, and I go to grade it, and I don't see a chart like this where you have the sum of your x and y components and you lay out the vectors, if I don't see that, at that point I quit grading that problem and you're going to miss all the points. I'm not even going to look at your answer. I am not even going to look at your answer. Because this is about a process. It's not about an answer. So you mark my words, tomorrow, if you go, hey, I want to get this problem, I don't need to write a chart. Guess what? I don't need to give you the points. Okay? So that's the deal. That's the roll of the dice you're going to take if I don't see this chart. And I'm not doing it to be a jerk. I'm doing it because it eliminates mistakes. Okay? So I got 4.76, so here's my 4.76, and here's my 2.5. And here's my sum. Now, I told you yesterday, how many significant digits do I want in all of those calculations we're defining the x and y components? Hunter, how many do I want? 3. I am appalled at the number of people that papers that I've already looked at, and the number of people that haven't put 3 significant digits. Again, I'm your boss. I say, hey, here's a simple instruction. I want everything to have 3 significant digits. I look at your paper. Guess what? You don't have 3 significant digits. What's going to happen to my frustration level? Way up. What's going to happen to your pay? It's going to go way down. Okay? It's a simple correlation. Follow simple instructions. Okay, now, I'm not worried about the numbers for now. Let's talk about this 4.76 at 195 degrees. Is my x component for 195 degrees going to be a positive or negative number?
Negative.
Negative. Okay. I don't care what the number is. I'll worry about the number later. What about the y component on my 476?
Negative.
That's also going to be negative. Okay. Cool. Now, my 2.5 over here. What about that x component? That's going to be positive. What about the y component?
Negative.
Now, so right away, what do I know about the sum of my y components?
Negative.
I know I'm going to end up with a negative number for my y component, which can only put me in which of 2 quadrants? I can only end up in the 3rd or 4th quadrant when I've got a negative y component. This is the only 2 games in town, which is going to match with what we said in terms of these values. Now, what do I know about my x component? Do I know which one that's going to be?
No.
I won't know until I add them up together. Okay? So, what does somebody have for the sum of their x components on this problem? Negative 2.14?
Yeah.
Yeah.
Everybody cool with this?
Yeah.
Yes.
Okay, if you're not, get cool. Now, what about the sum of your y components?
Negative 1.66.
Negative 1.66.
Yes.
Everybody cool with that?
Yes.
Beautiful. Brilliant. We're good. Now, I got a negative x and a negative y. Which component, which quadrant am I going to be in?
Bottom.
3rd? Now, here is the most important step that you have to do. And this is where the wheels fall off if you don't do this. Wheels will absolutely fall off the train. You need to come out here and take a second to make another little sketch. You go, oh, I got negative 2.14. I'll draw that x first, so that way you can find this angle relative to this x-axis. I got negative 2.14, and then I got negative 1.66. So, how are you going to find the result? Pythagorean theorem. 1.66 squared plus 2.14, whatever you get. That's easy peasy. Here's what gives you fits. Okay? This is what gives you fits. Is this angle right there. Okay? And where it is relative to the bigger picture. So, this is what I would do. Okay? This is what I would do. I would just find that angle using the inverse tangent of 1.66 over 2.14. I wouldn't worry about the fact that it's negative, wouldn't even jack with it. Okay? Not even on my radar screen, I don't care. All I'm going to do is I'm going to find this angle. That's all I'm going to worry about, right? So then, well, once I get that angle, is that my final answer?
No.
No, because I guarantee you this angle is going to be less than 90. And if I give this angle, where are you going to think it's going to be? I'm going to think it's somewhere over here. Okay? So that would be like saying, you know, you're pulling this way and I'm pulling this way, but we're going to go in that direction. Cool. Probably not going to happen. Okay? But so when I give that angle, what am I going to do? Add it to 180. This is why you have to make this sketch. Don't shortcut this step. Okay? I say again, don't shortcut that step. Okay? Cool with that? Everybody's groovy. So, that angle on number 5 on that C plus F should, now this is an ish, okay? Should be around 220. Okay, that's an ish. And your angle on that B plus E should be around 100. Okay, again, that's an ish. If you did 6 and 7 right, if you take your angle from 6 and add about 100 degrees to it, you should get your answer to your angle for number 7. That's an ish, but it's pretty close. Okay? We're good. Now, if you want to hold on to this assignment, hand it in tomorrow, you can. If you're done with it and you feel good about the process, go ahead and get it handed in. So, anything else? Once, twice, sold? Okay. So, Bad Mac, shut that down.
They like cracked them open at the same time. They like started drinking at the same time. That was good unison. Yeah, it's like, oh, they had
What
a
is this,
chug.
synchronized drinking?
Yeah, but the taste is so bad that it's hard for him to drink it.
What is it?
It's Switch.
Disgusting.
Yes, Garrett.
Why are you drinking?
I want to switch to another drink.
Yeah.
Yeah, pretty much.
It's
Then why are you
100%.
drinking?
Oh, it's so good.
Gary just showed
Those
us
are the
love.
biggest drinks everyone's drinking.
Garrett has the love. Gary
I
just
don't
showed
know.
that bad boy.
See, Garrett has
Are they
the
like an
big one.
energy drink?
I don't
No.
No, it's literally just sparkling juice that tastes
Yeah, I think
worse.
there's juice.
Want some?
I'm good.
Are you sure? How certain are you?
On a scale of 1 to
10.
100, I'm at like 99.9.
Oh, but
So
there's a chance.
still a chance.
So there's a
chance.
There's a chance.
But only if I'm dying of thirst in the desert.
We gotta get a desert.
Well, not urine.
Okay,
And I've
Google,
been faced
how
with
much
that
does renting a
situation.
desert cost?
What if he gives you money? What if he donates money?
I already donated a bunch of money.
Yeah, Matt has donated more money than anyone else in the class.
What'd you do?
Took a pair of pliers and a Swiss Army knife and rebuilt a wheel bearing in the middle of the desert on a truck.
But what'd you do when you were dying of thirst?
I never got to that point because I rebuilt the wheel bearing. So, but I was faced with it. That doesn't mean I died, you know. So, okay. Let's talk about the test. So what do you think is going to be on the test?
Vector.
Vector quantities. Okay? So, graphs. Graphs. Okay?
Scalar.
Might you think you might have to draw a tangent line on a position time graph? Oh, let's talk about position time graphs. Okay? Let's talk about position time graphs.
Please do.
So let's start with a simple true or false. True or false? If the slope of a velocity time graph changes sign, the object will change direction.
False. False.
Say it, repeat.
Okay. With feeling. True or false? If the slope of a velocity time graph changes sign, the object will change direction.
False.
Why?
It might just be slowing down.
It didn't stop.
Yes, so what?
So it didn't stop. And that you have to stop and change direction.
So, let's say that I've got a velocity time graph that's coming down here like this. True or false? The object is going forwards because it has positive velocity.
True.
You don't know which direction's forward, you just know it has positive velocity. Okay, so get out of your mind's the idea that positive velocity means you're going forward. Is the object accelerating?
Yes.
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 Yes. It just has negative acceleration.
Don't you mean it's
Yeah.
decent?
Don't you?
I know. It's
It's
designed to be
It's out of my head.
confusing. Like I know what it means.
Okay. You have to get out of your minds right now the thought that acceleration only means speeding up. What 3 ways can you make an object accelerate?
Speed up,
Slow
slow
down.
down. Speed up,
You can make it speed up
change direction.
or change direction. Because velocity is a vector quantity, which means it has what 2 things?
Magnitude and direction.
And
Direction
so what's the purpose of your gas pedal in terms of a velocity vector?
to increase,
Make the velocity vector get
Bigger.
bigger. What's the purpose of the brake?
to make it smaller,
Make it get smaller. What's the purpose of the steering wheel?
to change the direction.
Change the direction. Okay? Now, from here to here, this is the velocity, right, that's becoming bigger or smaller? Smaller. Do you think acceleration is a vector quantity or a scalar quantity?
Scalar.
How many vote that acceleration is a scalar quantity? Meaning that it only has magnitude.
You can change the direction, you can change the acceleration.
Think about the arrows. Let's think about the arrows. Okay? Shively. Okay. Here's the car, right? Here's the car. Which direction, and we're going to find this direction as being positive for the sake of argument, right? So this has some positive velocity vector. True? As the car is moving along, what's happening to that velocity vector? It's getting smaller, right? Because it's approaching 0. So we're slowing down, right? So there's like V1, there's like V2, there's like V3. So here's the question. My acceleration vectors are going to point one of 2 directions. They're either going to point in the same direction as my velocity vectors or the opposite direction of my velocity vectors.
Opposite.
Opposite. So if you're defining this direction as being positive, you're going to have negative acceleration. Oh, right. So can we represent acceleration in a direction?
Yes.
Yeah. Do you think it might have a magnitude?
Yeah.
Yeah. So therefore, you think it might be a
Vector quantity.
vector quantity. Just throwing that out there. Okay? So what have you hit in your controls of your car to make this happen? Hit the brakes, right? Or you've run out of gas. Let's just say that you hit the brakes. Now, At this point, I'm going to take this velocity vector and make it go up like this. Or velocity time graph and make it slope up like that. So now what have I done?
Hit the gas pedal
I've hit the gas pedal. Why?
because you're speeding up.
Because I'm speeding up. Oh, now what's going to happen to my velocity vectors?
And it get bigger.
They're going to get bigger. Okay, there's number 5. So now which direction did my acceleration vectors point?
With the
Positive. Oh, that's kind of cool, right? Because look, here I have negative acceleration with positive velocity, and I am slowing down. Here I have positive velocity with positive acceleration, and I am speeding up. But here's the question. At the bottom of that point, did I change direction?
No,
How do you know?
because you didn't cross the x-axis.
Velocity did not change sign. Did I change my acceleration?
yes.
Now, think this through. F equals ma. So, at this point, did I change the acceleration of the object?
Yes.
Very much so, right? I went from negative acceleration to positive acceleration. So if you look at F equals ma, what's the only way that I can change the acceleration?
Changing the force.
Change the force. Oh, did I change the force? Because what was applying the force up to this point?
Brake.
Great. Now what's happening?
Yes.
Change the force, I change the acceleration. Okay, that's kind of cool. Now, if I gave you this and said draw a position time graph that matches what's happening here, what would you draw? First off, where am I in terms of the reference point based upon my velocity time graph? It's a trick question.
I don't know.
I have absolutely no idea where I'm at in terms of this. All I know is that I have a positive velocity the entire time. I could be in Paris, I could be in Moscow, I could be in Dodge City, whatever. Doesn't make any difference. All I know is that I'm moving with some positive velocity. I don't know where I am in relation to the reference point. Okay, I don't know. So on my position time graph, I can say, all right, I'm just going to pick a point here. So let's say, whatever that is, a time 0, that's where I'm at. Okay, maybe that's at 20 meters. Okay? Could be at negative 20 meters, I don't know. I'm just going to arbitrarily pick a point. I'm at 20 meters, that's all I know. So here's my question. What would a position time graph look like to match that velocity time graph?
You're moving up. You're going up.
It's curving to the,
You're moving forward the entire time.
It would
Okay?
start to curve, but then shoot back up again.
It would be a low slope, and then it would increase.
All right, hold on. Let me kind of move that point down, since y'all were saying you want it to go up. Okay, so I'm here. So, is the slope going to be positive?
Yeah.
Yes.
So let's look at this. I'm going to give you the football curve. It could be this, it could be this, it could be that. The Mick Jagger lip curve.
Yeah.
Yeah. Okay, so which one?
It's gonna be top one.
Top one? You're solid on that one, huh?
Yeah.
You said that with authority.
it is.
Yeah, it is.
It
Well,
is.
because
Until it,
it starts with a higher velocity over on there, but then it starts to slow down.
Okay, why can't it be the middle of the lips?
It's not
It's not constant. We know it can't be this. This one's making it do what?
Speed up.
Speed up. Is that what's happening?
No.
No. So that leaves us with,
The top of the
Slowing
Mick
down.
Jagger.
now, slowing down. Okay, so I got that. Does it flatten out completely?
No.
Why not?
because it's never constant.
It doesn't ever stop, right? How do you know it doesn't stop?
It doesn't hit the x-axis.
Never hit 0.
Yes.
Now, am I slowing down?
Yes.
But I don't stop. Okay? So I don't want this thing to plateau out. Okay? I want to have it some curve like that. Right? Approaching it, right? But then how can I show this happen?
Mick Jagger's bottom lip.
We go from the top lip to
Bottom lip.
the bottom lip.
Yeah.
Okay? That's not bad. Okay? So Now, here's what I'm gonna do on the test tomorrow. This is where, mark my words. I'm gonna say, okay, find the slope of Mick Jagger's lips at the 8-second mark. So what are you gonna do?
Tangent.
What are you gonna use to find
Ruler.
ruler? You hear me?
Yeah.
A griddle? Uh-huh.
Riddle.
So, you're gonna come in here and you're gonna draw a tangent line. And how many points is that tangent line gonna touch the curve?
1.
One. How many points do you need to find the slope of that?
2.
2. Think you're gonna show your work?
Yes.
What units is that slope gonna have?
Meters per
Meters
second.
per second. And that's gonna give you what?
Velocity.
Specific type of velocity. Instantaneous velocity. Okay? It's going to give you instantaneous velocity. Now, here's my position time graph. Could I, students of mine, find this area?
I mean, you could, but it wouldn't give anything relevant, right?
Kind of like talking to a freshman. You could talk to her, but it's not relevant.
Yeah.
Why?
Because wouldn't it give you only like meters seconds or something like that?
Yeah, you're going to get some information from the freshman, but is it relevant to your life?
No.
No. He's going to talk blah, 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 blah. Okay, that's all you're going to do.
Yeah.
Because look, what you at the end of the day, this is in meters, right? And this is going to be in seconds. So when you multiply meters times seconds, what units do you get?
Meters seconds.
You don't get meters per second. Love of God, no, it's not meters per second.
Meters
Meters
seconds.
You get meter seconds. What's measured in meter seconds? Nothing.
Widgets.
Butkus. Okay? It has no meter. Now, on your velocity time graph, could you find that area?
Yeah.
Yeah. Yeah. Because that gives you
Displacement.
displacement. Oh, that's nice. That's nice. Okay. Now, what if I take a velocity time graph and do this?
Yes.
There's 0. Now, does that change direction?
Yes.
How do you know?
Slow down. Stop.
So what are you doing up to this point?
Slowing down.
Slowing down. Nice. Okay? Because you're approaching 0. Now, do you continue to slow down once you cross 0?
No.
Yeah, you can't slow
You're
down
approaching 0.
0.
Your
It's like,
velocity.
I'm going to
your
stop.
velocity
Now
is
slow down even more. No. Okay? But what is going to happen? You're going to speed up. Is your direction going to change?
Yes.
Yes. Okay. So how can I draw this on a position time graph?
Well, you'd have to, at one point, it'd have to plateau.
Why?
Because it crossed 0, so it stopped.
So it's got a plateau.
Yes.
Okay?
It wouldn't plateau though, because it doesn't stay
So
at
here's
0.
0,
It just hits it and goes
right?
away.
What's our reference point?
I don't know. You pick one. Let's just say, for the sake of argument, okay, that I'm going to start at, but here's the deal. What's my initial velocity going to be?
Negative.
We don't know.
Sure, dude.
We know it's going
Well,
to be
is it
negative.
going to be positive or negative?
Negative.
Oh, negative.
Negative, okay? So let's start here with something like positive velocity, right? Okay? There's some positive velocities, there's some negative velocity. Excuse me, positions, my bad. Position. My bad. Back off. Mark her out, okay? So here's some positive position, here's some negative position. So I know I'm going to have a negative velocity, so let's say I'm going to start up here. So what's this line going to do?
Start going down towards the reference point.
So we'll do the Mick Jagger lips curve.
Yeah.
So top lip, bottom lip, middle lip.
Bottom lip. Bottom lip.
Definitely not.
Definitely not in the middle. Why? Because if a straight sloping line here corresponds with what over here?
Horizontal.
Horizontal. Okay? So straight here, horizontal here. not straight, therefore this has to curve. Question is, do we curve down? Do we curve up?
Curve down.
Curve down. Bottom lip. Why?
Because velocity.
Slowing down. Okay, that's kind of cool. All right. So we're to here, right? Slowing down. At this point, right here.
Yeah.
100, what was this?
Bam.
Plateaus.
Yeah.
Maybe where we could maybe draw a tangent line that might have a slope of 0. International sign for tangent line with a slope of 0. You a ninja.
Yeah.
Okay.
Nowhere close to
Let me tell you the best ninja story I've got. So that's a true story. So, the school that I taught at, most of the kids actually lived at the school. It was a boarding school. Because Brooklyn is about the size of Texas, but there were only like 20 high schools at the time. So imagine 20 high schools in the entire state of Texas. And so if you were in the remote regions, it wasn't practical to drive, or because nobody had cars anyway, or buses. So the idea of busing you to school didn't exist. You walked or you lived out to school. So, and I also coached the softball team. It was both boys and girls played softball, but it was fast pitch, underhand. And so it was a Saturday morning, and most of my softball players lived out at school. They were boarding students. And there was like one common room where they had like a television and I had a VCR. My softball players loved to watch ninja movies. So I'm walking, Saturday morning, I'm walking up to the school, and I stop, and I go, Mr. Burkett, hi. So I'm stopping. And I'm watching the show, and I start to laugh, because it's a midget ninja, okay? Which in and of itself is funny. But he would like run up and like jump, like run up a tree and then flip in the air and then land behind him and then start like hitting him in the backs of the legs. And I'm just laughing. And my team is getting upset with me. Oh, teacher, why do you laugh? I said, it's a midget ninja. How can you not laugh at a midget ninja? Come on. Ah, teacher, this is real. Oh, for the love of... I said, no, it's not. And I said, they go, it is real. I said, no, it's not. And we got into this argument. And so I said, okay, look. I said, when I move my hands like this, because if you've ever seen any cheesy ninja movie, when they move their hands, they make a sound like, okay? And I said, when I do this, do you hear anything? And they said, no. And I said, you know why? Honestly, this is the truth. It's the best logic I've ever heard. I said, do you hear anything? They said, no. And I said, why? They go, because you are not ninja. Valid point. Yep. So if I was ninja and I did this, you would hear like sounds. And so when Hunter was back there going, it was like reminded me of midget ninjas in Africa. So if you were a ninja, it would make a sound. So
It was pretty cut.
You're pretty good at softball.
huh?
You're pretty good at softball. It's pretty good.
Nah, it wasn't bad. Okay. So we got ninja sets. Okay. So what's this? What's this line going to do from here? At some point, remind me to tell you the dead chicken story.
I had chickens.
Going to do this?
Yeah. Is that the bottom lip of Mick Jagger again?
Yeah.
Okay.
Is that two bottom lips?
Yeah, it's Mick Jagger's cousin. All right. Go with this. Does this match this?
Yes.
Yeah.
Is there a direction change? Does the
Yes.
velocity go to 0?
Yes.
Yes.
True or false? True or false? If the slope of the position time graph becomes horizontal, okay, the object changes direction.
False.
False.
Could be true. but
Well,
also
it
say
depends on what happens after it stops.
Okay, why is it false?
Because it hasn't sped up and it hasn't.
Mary?
It hasn't sped up.
Okay? So like if I took that position time graph and just did that, does that mean that it changed direction?
No.
What did it do?
It stopped.
It just stopped. Now, if it comes down like this, then did it change direction?
No.
No, why?
Well,
Well,
it,
it's sped
It's
up.
sped up.
it
It's
just
just
didn't, it didn't
It's going in the same
go
direction.
in the direction, the
And
slope
change
still has
sign.
the
The
same
slope
sign.
actually changed sign.
No.
No. Now, if I bring it up like this, then is there a direction change?
Yeah, it is.
All day long, okay? So just because this goes to 0 does not mean that you change direction. Now, can you change direction without it going to 0? No.
No.
Okay, so that's the dichotomy. Just because it goes to 0 doesn't mean that you change direction. But you can't change direction without the velocity going to
0.
0. Okay? Cool with that. All right. Now, here's another type of problem I promise you is going to be on the test. You mark my words. It's going to be using this equation that displacement equals velocity times time. Promise you. You're going to have problems like this. You mark my words. So here's what I'm going to do. I'm going to say something like this. I don't know. A car is moving at 30 meters per second, and I want to know how long it's going to take to travel 60 meters. Okay? So the time is going to be what? Now, this is one of those deals. You need to look at this from a couple of perspectives. First off, what's the only time you can use displacement equals velocity times time?
Isn't it like a constant velocity?
When you have constant velocity, okay? Because here's the problem, if your velocity is changing, guess what? You don't know which number to use, okay? Do I use 0, do I use 5, do I use 15? I don't know. So this is a cool equation, but you can only use it when you have constant velocity. Now, I got 30 meters per second for 60 meters, right? I want to know how long it's going to take to travel that 60 meters. Now, just step back and think about this for just a second. This is all I ask for just a second. Olivia, is my time going to be bigger or smaller than 1 second? Based upon the fact that I'm traveling 30 meters per second. Is my answer going to be more than a second or less than a second?
More,
You say that with no confidence.
more,
Why?
because you're traveling 30 meters in 1 second,
Ah! And the distance that I have to travel is more than,
30 meters.
so therefore I have to end up with more than.
30, then 1 second.
Ah, nice, nice. Okay, well done. Okay, so before I even start the problem, I'm going to look at this and go, wow, my answer has to be more than a second. If I get an answer less than a second, I've done something wrong. Now, this is what you all are going to do wrong. Okay, do not do what I'm about to do, but this is what you all are going to do wrong. And y'all sit here today and go, oh, Mr. Burkamp, we won't do that. You lie. Here's what you're going to do. You're going to take 30 meters per second, and you're going to divide that by 60 meters, and you're going to go, oh, that's a half a second. You mark my words, that's what you're going to do wrong. Now, why is that wrong for so many number of reasons?
That give you meters over meters seconds.
First off, does this produce units of seconds?
It's meters over meters seconds. Right?
What?
No,
What?
you just see the inverse.
No.
Yeah, 1 over second.
Wait. Oh,
Meters
sorry.
per second times 1 over meters. True?
Yeah.
No.
It's 1
Oh,
over second.
yeah.
Yeah.
Yeah. I was saying the same thing. I just forgot to cancel it.
So here's my question. Is 1 over seconds the same as seconds?
No.
Now, listen to me. Listen, and I've seen this more times than I ever want to admit. I've seen kids go through and they get units of 1 over seconds. They know it's wrong. And I've seen this happen. So what they do is they erase the 1 over seconds. And it's like, okay, it's not there. And then they'll come up here and they'll put seconds up there. It's like they know it's wrong. And they think erasing it will fix it. Because if I just put seconds, it's all good. Because that's what Burkham's want is time. He wants seconds. It's all good. No. If your units do not produce what you want, something is wrong. And you erasing it and writing seconds isn't going to fix it. So as you're going through the test, literally, if you don't get seconds, stop. okay? And don't erase it and then go, oh, I'll just write it down anyway. No, okay? Make the units work out. I beg of you. But this is what you're going to do wrong. Now, allowing for what Olivia thought through, right away, why do you know this is wrong?
It's less than a second.
It's less than a second. So this is why you step back and you look at a problem before you even try and figure it out. Oh, okay, my answer's got to be more than 2 seconds. Well, that's just jacked up because I have less than a second. Because here's what you all did. You did meters per second and divided it by meters. Now, what if you did this? And let's say that you're an equation kind of person. Oh, this is cool. I know how far I'm going to go. I want to find time. So what are you going to do?
Divide by velocity.
Yeah, I'm going to take distance and divide it by velocity. Now, when I take 60 meters, and I divide that by 30 meters per second. Now, Olivia, why does this make you happy?
Because it's more than a second.
Ah, there you go. Okay. Now, why am I happy?
Because you're gonna end up
I'm going to end up with seconds and not,
inverse.
yes, because the seconds are going to flip up. And I think the thought process is that you all see seconds up here and you think you get seconds because it's up on top. But in reality, you get 1/4 seconds. You don't get seconds. So just pay attention to that. Now, that's if you're a formula kind of person. It's like, oh, Mr. WordCamp, I love formulas. Oh, this is so cool. Nerd, but it works. Okay. Now, what's another way that I could approach that same problem? How would I show that on a velocity time graph? How would I show a constant 30 meters per second velocity? Pretty does that, okay? Not the full, just boom, okay? The volleyball player, then, just boom, that's it. So, here we are at 30 meters per second. Now, how does the 60 meters play into this problem?
It's the displacement, so it's that times.
That's your displacement, right? So that's this area here of 60 meters. So, if you're a geometry person, what am I asking you to find? I know you've got the area, that's 60 meters. And you know the height is 30 meters per second.
You want the,
I want the width, I want this dimension here, right? Which is going to be the time. Because if you think about it, displacement equals velocity times time. That's like saying area equals length times width. Because what does the area on a velocity time graph give you? Displacement, which is velocity times time, which is the length and width of the rectangle on a velocity time graph. Oh, that's kind of cool, right? So basically, you know the area is 60 meters. You know one dimension is 30, solve for the other one. There you go. So if you're a geometry person, you can approach the problem this way. The other thing you can do is like, oh, Mr. WordCamp, I love ratios. Oh, I just love ratios. Okay. What does 30 meters per second mean?
30 meters per
In 1 second,
You go 30.
Olivia,
You go 30 meters.
beautiful. So I can go 30 meters over 1 second. Guess what? That's going to equal 60 meters over X number of seconds. So then what are you going to do?
Solve for it.
Cross multiply and divide. So, guess what? You're going to get 2 seconds. So, you could either approach it as an area problem, if you're into geometry. You can approach it as a formula problem, if you're into formulas. Or you can approach it as a ratio problem, if you're into ratios. I don't care. Pick one. It doesn't make any difference. But guess what? What do you think you're going to have to show? Work. Y'all are learning. I like that. Let me see what else is randomly do I have on here. Let me see. That's about it. We got the big things. Okay. Anything else you want me to go over? Make sure everybody's cool with? Yes.
I bet you already went over this, but displacement versus distance.
Okay. So here's the classic thing. remember when we did the deal when we were going to Kansas City?
Yeah.
Okay? And here was Wichita, and here was Kansas City. And we made that the reference point, and that was 300. So, displacement is a vector quantity, which means it has magnitude and direction. So, if I said, what's the displacement to Kansas City? You would take position final minus position initial, and you would get 300. Okay? Now, if I said, what's the displacement from Kansas City to Wichita? Okay? Then the displacement would be position final minus position initial. So if you're going that way, that displacement is a negative 300 kilometers. So your displacement going in one direction would be a positive number, because that's a vector quantity. The other one would be a negative number, because you've changed that direction. Now, if I said, hey, how far is it to Kansas City? You just say 300 kilometers. But if I say, how far is it from Kansas City to Wichita? You're just going to say 300. So distance is a scalar quantity. It's just a number. Because you're not telling me which direction that you're going. But as soon as you define it on a number line, then it becomes displacement. Okay? It's like this. What is speed, a vector quantity or a scalar quantity?
Scalar.
Scalar, okay? You have a speedometer, right? So if I said, Jones, how fast are you going typically when you drive to school?
46.
46. 46, not 45, 46.
Yeah, 46, 47.
Okay, let's go with 46, okay? I like even numbers better than I do odd, especially 47 being the prime number. So let's go with 46. Do I know which direction that she's going?
No.
All I know is that Jones on average drives 46 miles an hour. She could be in a helicopter descending from on high. She could be burrowing up from underneath the ground. I don't know. She could be driving east, west, south. I don't know. All I know is that on average, this girl drives 46 miles per hour. Now, how could you make that a vector quantity? Yes?
I thought I can like tell you like where like what the direction like it's.
Yes. So on average, you drive 46 miles per hour north. Now it becomes a vector quantity. Okay? Now I know, not only do I know how fast she's going, now I know the direction that she's going. Okay? See the difference. Mass, scalar quantity, vector quantity.
Scalar.
Scalar. What's your mass? 5 kilograms. It doesn't make any sense to say, oh, it's 5 kilograms north. Okay? It's just 5 kilograms. That's it. Okay. Anything else? What are you going to bring tomorrow? A tractor and a? Nice.
Any kind
So then the total displacement of that would just be 0.
Traditionally, yeah, the total displacement would be 0. Now, quick refresher. How do you calculate average velocity?
Position.
Position final minus
Position.
over
Time.
time. Okay? So, like, let's say that you have a position time graph that looks something like this, and I say, hey, calculate the average velocity over this interval. So what's your final position going to be?
0.
Initial position would be like 2 or whatever it is. So you'd have 0 minus 2, and then you divide that by the number of intervals in between. Okay? Go with that. Anything else? Okay. So here's what you're going to get. You're going to get, and this is going to happen with every test from here on out. So you've got a review, okay? This one is just one-sided. And I'm also going to give you the answer key to the review. Now, let me explain how not to use this material. Number one, it's not for a grade. You're not going to hand this in. I'm giving you the answers, okay? I'm giving you the answers. Love y'all to death, but I'm not going to take a grade when I give you all the answers. So, here's how you don't study. Don't read this first question and go, can a car change direction, da-da-da-da-da. And then read my answer and go, wow, Burkham's smart. He got that one right. That's exactly right. He's a genius. And then you look at number 2, which is a math problem, and you look at that and go, Yep, that's exactly how I would work that problem the same way. Point, work in square. Okay, no, okay? No. This is a thought process. What I would do, if I were you all, I wouldn't even breathe on this sheet until you've completely worked this sheet. Okay, it's the best advice I can give you. Best advice. Because when you look at mine, you're immediately biased on how to solve the problem. Okay? So I would not look at this until you get completely done. Now, if you take this review and you read through this and you can only work like a third of the problems, we have a problem, Houston. Okay? This is the review. All of this should be familiar to you. If it's not, this is an opportunity for you to go, oh, maybe I ought to refresh myself on that terminology. You have all of your stuff back, like that assignment 2-1, the labs, that type of thing. Go back, and if you see something that you've done wrong, fix it. Figure out what went south on the stuff that you have back. I promise you, that cart lab where it bounces off the wall, I promise you, I'm going to ask you questions on it. So I might say something like this, okay? Here's the velocity time graph. And let's just say, for the sake of argument, that it does something like this. Okay? So here's the velocity time graph. And I might say, okay, and we'll label this A, B, C, and D. And I might say, okay, in which regions is that cart speeding up?
A, C,
A, C,
and that's it.
yeah,
Just A and C.
Just A and C.
yeah.
Yes.
You sure?
Yes.
Why?
Because
Speed
this,
is
it doesn't,
Yeah, it's going.
Probably
So
less
it's
slow.
it's not
So its
just
velocity is
Okay,
increasing.
it's going away from
zero.
0. So here it's speeding up, and then C is also speeding up. But do A and C have the same direction?
No.
No. Okay? One's going in one direction, the other one's going in the other direction. In which region or regions is the object accelerating?
All of them.
All of them. Why?
Because
Felix, why is it accelerating in every region? Because what?
Why?
Felix, how do you show constant velocity on a velocity time graph? You're thinking acceleration. This is a velocity time graph, right? So what would a horizontal line show? Okay, so if I got a horizontal line, that means my velocity is constant. So are any of these lines ever horizontal? So is it ever not accelerating? No, okay? And again, get out of your minds the idea that when I talk about acceleration on the test, am I only talking about speeding up? No, I could be, just acceleration is just changing velocity. That's the biggest leap of faith that you have to take. So it's accelerating the entire time. Under which region or regions is it undergoing the biggest acceleration?
B to C.
B and C, why?
That's when it hits them.
That's just, what are you going to look for to find the biggest acceleration?
the steepest
biggest
slope.
Big bam.
The biggest change in the smallest amount of
steepest
time.
slope.
Yeah, or the biggest change in the smallest amount of time, or the steepest slope. Okay? When's it slowing down?
And D.
And B. And B. Right? Why?
Because they're approaching.
Because they're approaching
You're
zero.
approaching 0. Okay? That's the type of thing that you've got to be able to do. All right? So in which regions do you think the spring is in contact with the wall?
B and C.
Why?
Because that's where it's direction.
Yeah, that's the biggest change in velocity in the
Biggest.
smallest amount of time. Okay? All right. So we're cool with that. So as you're preparing this, so help me, when you hand in the test tomorrow, if you have not drawn a tangent line and found the slope, something's wrong. If you haven't drawn a chart with the x and y components on it, with two vectors, you've done something wrong, okay? If you have not looked at a position time graph and a velocity time graph and figured out what's going on, you have done something wrong. If you haven't used distance equals velocity times time, you've done something wrong. So guess what? All of those are on this sheet. So don't go home, lay everything out, put on your headphones, check your phone and go, what are you doing? I'm studying. No, you're not, okay? This requires some thought. You work through the problems. If you don't know how to do any of these problems, this is why you've got this, then come back and work that problem like an hour later so that it becomes automatic, okay? It has to become automatic. Jones didn't get to be as good a basketball player as she is by walking out, shooting one free throw and go, oh, I got this, I'm done, okay? It becomes repetition. That's the biggest thing I can tell you to do. When I was studying like physics, math classes, I would work problems, excuse me, again and again and again until it just became automatic. Then I changed the numbers and then I worked the problems again and again and again so that it just becomes, okay, I'm going to do this, I'm going to do this, I'm going to do this, okay? Now, with the vector quantities, you know, and again, you've got to be able, you have to remember what you have available to you. If I said, okay, here's 20 meters per second at an angle of 30 degrees. Do you have on your equation sheet, oh, the y component is the velocity times the sine of the angle? Is that anywhere on your equation sheet? No. What do you have on your equation sheet? The definitions of sine, cosine, and tangent. Okay? So the idea that you're gonna, that y is gonna equal the velocity vector times the sine of the angle, that is not on your equation sheet. It's not there. But if you know your trig functions, then it is there. Okay? I'm done. What you do with the rest of the time is up to you. But that tomorrow will be the first kind of big-ish test. So, call it good.